All right, everybody. We are going to get started with a little bit of review before we jump into our example. Oops, my lights just turned off. There we go. All right. So if you want to go to the third screen, that's where we're going to start off today. It is the check conditions screen. If you're navigating through here, it starts with in chapter 8 at the top of the screen. All right, so again, we have our 3 conditions that we have to check before performing a significance test. So before we do the math, we have to check conditions. Right, it is part of our state plan do conclude 4-step process that we should be doing anytime we're solving a problem about significance tests or confidence intervals as well, right? Those both have our 4-step process, okay, where we're using a method of inference, right? With performing a significance test about a population, we must check the conditions that it is random, the 10% condition is satisfied when sampling without replacement, and that the large counts condition has been satisfied, right? Meaning there's more than 10 or at least 10 successes and failures in our sample, depending on how we're defining a success or a failure. Right, so random, 10%, large counts. Right, same 3 conditions we had to check for confidence interval. All right. The next thing we're going to look at is the one sample z-test for a proportion. This is our inference method when doing a test about a population proportion. It is the one sample z-test. All right, we're going to choose an SRS of size n from a large population that contains an unknown proportion p of successes to test the hypothesis h naught such that p equals p sub 0. Compute the z statistic. We have z equals p hat, our sample proportion, minus essentially the assumed proportion from our null hypothesis, divided by the square root of the proportion from the null hypothesis times 1 minus that proportion divided by n. Please notice that this entire fraction is under the square root sign, meaning we're taking the square root of whatever we get in this fraction. It's not just the square root of the top part, it's not just the square root of the bottom part, it's the whole thing. Okay. We're going to find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis, HA. We do this again by using table A. Okay, we'll find that z-score on table A, find the proportion. We need to make sure that we're finding the proportion related to our alternative hypothesis, greater than, less than, or just not equal to, in which case we have symmetry and we just double either the greater than or less than proportion. And we have this graph here as a reminder. All right, so essentially the state of our 4-step process is stating what we want to find. Plan is where we say the inference method we're going to use, one sample z-test for a proportion, right? We check our conditions, random, 10%, large counts, and then we do the one sample z-test, right? The do part is the calculation. We're going to find the z-score and then use that z, the z statistic, to find the proportion using table A. Okay. Is there any questions so far? Anything I can clarify? We'll see an example of all this shortly, but is there anything I can clarify? Okay. Again, the last thing we're going to look at is our 4-step process that I've been stressing already. All right, to perform a significance test, we state hypotheses, check conditions, calculate the test statistic and p-value, and draw a conclusion in the context of the problem. All right, the 4-step process is ideal for organizing our work. That's why we use it. State, what hypotheses do you want to test? right? And at what significance level? Define any parameters. Right? Plan, choose the appropriate inference method, check conditions. Do, if the conditions are met, perform calculations, compute the test statistic, find the p-value, conclude, make a decision about the hypotheses in the context of the problem. Right? Do we have evidence that supports our alternative or that it doesn't support? Do we reject the null hypothesis or do we fail to reject the null hypothesis? Okay, so that's kind of the in a nutshell review. Those are the things we need. Okay, so now we're moving on to a practice problem. This is screen 12, so you should all move to screen 12 so you can see what's going on. So again, everyone should be on screen 12. There we go, we're almost there. All right, most of us are there. So here is screen 12. All right, side effects. Practice with the 4-step process. So this problem should use the 4-step process. You should stay organized. You should do this on a piece of paper. All right. A drug manufacturer claims that less than 10% of patients who took its new drug for treating Alzheimer's disease will experience nausea. To test this claim, researchers conduct an experiment. They give the new drug to a random sample of 300 out of 5,000 Alzheimer's patients whose families have given informed consent for the patients to participate in the study. In all, 25 of the subjects experienced nausea. Use the data to perform a test of the drug manufacturer's claim at the alpha equals 0.05 significance level. Right here, I do have a link to the formula sheet and tables. And I recommend doing your work on paper and then uploading a picture of your work using the upload image option in the bottom left corner of the text entry box. Okay, so it should look like this. You have your image thing here if you want to do that. All right. You can also type into the text entry. That's up to you. So then we are going to talk about this. All right, let me turn off again. There we go. So here we go, guys. This is our 4-step process. If you look at the shared screen in Teams, I have OneNote pulled up with basically how we can do this problem. All right, we have the first thing that I chose to do is just list out the information I have. All right, so I have my null hypothesis, my alternative, all right, the sample size, N. I actually am given the population size that I'm pulling the sample from. That's 5,000. All right. My sample proportion is 25 out of 300, so I get 0.083, and this is actually a repeating decimal, 0.0833333. I just rounded to 0.083. And my significance alpha level is 0.05. Right? This is just for me to have all my information in one spot. Right? It is not necessarily part of the 4 steps. It's just a starting point for me so that I have everything I need. Right? So then we go to state. We want to perform a significance test on the hypotheses H naught such that P equals 0.1 versus HA such that P is less than 0.1. Right? Because the thing that we're curious about is there less than 10% that are getting nauseous from this drug? Right? Because that's what we want. We want there to be less than 10%. Right? P is the true proportion of the 5,000 Alzheimer's patients who would experience nausea while taking the drug. Right? And we're testing at an alpha equals 0.05 significance level. So this is all stating what I'm going to be doing. It gives all the information to the reader I'll do a significance test. These are my hypotheses. This is what P represents, and here's my significance level. The next part is the plan step. Right? If conditions are met, we will do a one sample z-test. All right, so we have, let's use this, kind of this first statement here, if conditions are met. All right, saying, so we're going to check if for conditions are met, and then we will do the one sample z-test for the population proportion, P. The one sample z-test is the inference method. All right, we're saying what method we're going to use. This is an inference method because this allows us to quantify things in a way that I can make an inference about the entire population. So we check our conditions. We have random. The sample was chosen randomly. We were told that. 10%. All right, 300 out of 5,000 is 0.06, which is less than 0.10. So it's less than 10%. We're good to go. That condition has been met. All right, so we're good here. We're good here. We have our large counts. 0.1 times 300 is 30, which is greater than or equal to 10. And 0.9 times 300 equals 270, which is also greater than or equal to 10. We're good. So now we've planned, we've done our checking of conditions. Now we're going to do the work. All right, doing the work we have to do the two things. We find our test statistic. Which in this case is the Z statistic. And we find our p-value based on our test statistic. That's the two things we're doing in our do phase, right? So Z equals p hat minus p divided by the square root of p naught times 1 minus p naught divided by n. So we get 0.083 minus 0.1 divided by the square root of 0.1 times 0.9 divided by 300. And again, this whole thing is under the square root sign. All right, so we're taking the square root of that entire fraction. And we get approximately negative 0.98. All right, we then get a p-value, right, because we're looking at less than. Right, I don't need to do anything with the z value. I don't have to do the complement rule. I just do the probability of z being less than negative 0.98 on table A. We get 0.1635. All right, our p-value is greater than 0.05, which means we failed to reject the null hypothesis. All right, this is not a conclusion. This is just me finishing the do part so that I have something to make a conclusion off of. Right? This is just some of my scratch work. Right? The next part of this is the conclusion where we write conclude. Right? Because the p-value 0.1635 is greater than alpha equaling 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that the true proportion of these 5,000 Alzheimer's patients who would experience nausea while taking the new drug will be less than 10%. All right, I give a nice explanation, right, stating what this means in the context of the original problem. All right. Now, we can also use the calculator. All right, and in this case, we're going to go to stat, and we have this tests all the way to the right. We're going to scroll to the right. We're going to do number 5 here, the one proportion z-test. because that's what we have. Essentially, it's like the one sample z-test. All right, so we'll go there, we'll hit enter. All right, I've already filled this in with our information here. So the P naught is 0.1, right? That's our hypothesis, our null hypothesis proportion. X here represents the number of successes, right? The patients who did not experience nausea. In this case, we had 20, or the patients who did experience nausea, which was 25 out of 300. We have 25 here for X, N is 300. That was the sample size. And here where it says proportion, we can say proportion is not equal to the hypothesis, less than hypothesis, or greater than hypothesis. We've selected less than because that's our alternative, is to be less than. All right, so now that this is all filled in, we'll hit calculate. All right, it gives us the Z value of negative 0.96225, blah, blah, blah. Notice that it's slightly different than what I got here, calculating it by hand. And this is just due to some rounding, right? I have to round the 0.083. And this fraction here is probably has some rounding error in it as well, right? And we get 0.98 here, we get 0.962 here. They're really close. Again, it's a rounding issue, right? That gives us a p-value here of 0.1679, right? About 0.168, right? Where I get 0.163 or 0.164 if you round to 3 spots, right? P hat is the same, N is that, but it gives us kind of these results a little faster, right? And again, if you're using one of these calculator functions, you need to explicitly write that out on your test to say, hey, I'm using the one proportion z-test on the calculator. These are my inputs. This is what I got. So we get pretty close to the same results. Ultimately, we get the same conclusion from either the calculator or using table A. And both are valid to use. Is there anything I can clarify? Any questions you have? Okay. All right, we're going to go back to this and move on to the next screen here. Type 2 error and the power of a test. A significant test makes a type 2 error when it fails to reject a null hypothesis, H naught, that really is false. There are many values of the parameter that make the alternative hypothesis true, so we concentrate on one value. The probability of making a type 2 error depends on several factors, including the actual value of the parameter. A high probability of type 2 error for a specific alternative parameter value means that the test is not sensitive enough to usually detect that alternative. All right. So the power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specified alternative value of the parameter is true. So essentially, the power of a test tells us whether or not what we're doing is sensitive enough to give us the proper rejection of the null hypothesis when the alternative is true. A higher power gives us essentially more confidence that our test will tell us the correct outcome, right? Whether to reject or fail to reject. Mostly having to do with rejecting the null hypothesis because the alternative is true. All right, and to help with this, we're actually gonna look at a AP Daily video, a little section of it that helps explain this idea a little better than I can. So let's see if this will work for me today. right, cool. And hopefully this will work. All right, guys, you gotta let me know if you're able to hear this. I think I set it up right, but if you can't hear it, please tell me.
Now let's talk about power and type 2 errors. In many contexts, a type 2 error is more consequential. I say this because in most research, researchers are trying to show that the alternative is true. And if they make a type 2 error, that means they didn't find convincing evidence the alternative is true, when it really is. So their suspicions were correct, they just didn't get the data to back up their suspicions. So for a researcher, a type 2 error is really bad news. Well, they came up with a word to talk about the probability of avoiding a type 2 error, and that word is power. So power is the probability of avoiding a type 2 error. The power of a test, then, is the probability that a test will correctly reject a false null hypothesis. Notice it says correctly there. Power is describes a correct decision. So the null hypothesis is false, and our data suggests that it's false, gives us convincing evidence that it's false. So power is the probability that we find convincing evidence for the alternative when the alternative really is true. That means the probability of a type 2 error is 1 minus the power. Remember, if power is the probability we avoid a type 2 error, then 1 minus the power is the probability of a type 2 error. Now let's look at an example to put this in context. To investigate if high school students associate the color green with being more natural, 2 student researchers randomly selected 30 students from their school. Each student was asked to taste 2 cups of lemonade in random order and state which one tasted more natural. One of the cups was green and the other cup was white. And unknown to the taste testers was the fact that both cups contained the same brand of lemonade. From previous videos, remember that we talked about the null hypothesis being p equals 0.5 and the alternative p greater than 0.5. where p is the proportion of all students at this school who would choose the green cup. Now, suppose that researchers used a significance level of 0.05 and that the power of the test against an alternative of p equals 0.64 is 0.45. Interpret the power in context, then find the probability of a type 1 and a type 2 error. So before we answer these questions, I want to reread the question because that first sentence might sound a little confusing. It says, suppose that the researchers used a significance level of 0.05. Well, that's pretty standard. And that the power of the test against an alternative of p equals 0.64 is 0.45. So we're saying the power is 0.45, and it's that number for the specific case that the truth is 0.64. We're not going to get into the calculations in this video, but the calculation of power depends on what the true value is, if it's something different than the null. So in this case, we're assuming the true value is 0.64, and then we've done calculations to show that the power equals to 0.45. Again, you don't need to worry about where those numbers come from. I just want to make sure you understand what it's describing. So interpret the power in context, and then we'll find the probability of a type 1 and a type 2 error. So here's what the power means. If the true proportion of students who would choose the green cup is 0.64, then there's a 0.45 probability that we find convincing evidence that more than 50% of students would choose the green cup. In other words, there's a 45% chance that we'd find convincing evidence for the alternative hypothesis. Now, as far as the probabilities, the probability of a type 1 error is equal to the significance level. That's easy, 0.05. And the probability of a type 2 error is 1 minus the power. So remember, power is 0.45, and so the probability of a type 2 error is 1 minus 0.45, or 0.55. Now let's talk about what fact.
All right. So there is that. So that hopefully helps make a little bit more sense of what a type 2 error and the power of a test are and how they're related. Essentially we want a higher power to help give us confidence that we're going to correctly identify or correctly reject the null hypothesis when the alternative is true. Okay. Is there any questions or clarification I can give on this? And so again, this just kind of helps sum this up a little bit. It's very similar to what we just saw. The significance level of a test is the probability of reaching the wrong conclusion when the null hypothesis is true. The power of a test to detect a specific alternative is the probability of reaching the right conclusion when the alternative is true. We can just as easily describe the test by giving the probability of making a type 2 error, sometimes called beta. That's fancy looking Greek B. Power in type 2 error, the power of a test against any alternative is 1 minus the probability of a type 2 error for the alternative. That is, power equals 1 minus beta. We also saw that the probability of a type 2 error is 1 minus the power, right? They are complements of each other. Right. How to increase the power of a significance test. We can increase the power of a significance test by increasing the sample size or increasing the significance level. We can also increase the difference between the null and alternative parameter values that is important to detect. This difference you usually have little to no control over. Unless you're the person running the experiment and you're choosing to make these adjustments, you really can't change what the null and alternative values are, right? If you're provided a problem, you don't have the authority to change those values. So really, the methods we can use would be increasing the sample size or increasing the significance level. Right, so this is how we can increase the power, which again, increasing the power allows us to correctly reject the null and have evidence for the alternative when it is true. All right. So then we're on to, oh no, I messed up. I forgot to give you guys a place that you can actually write stuff in here, so that was silly. So for this one, please just write your ideas down on a piece of paper and then we'll talk about it in a short minute. But anyway, we have the same problem that we saw too on slide 12. All right. For A, describe a type 1 error and type 2 error in this setting and explain the consequences of each. Okay. The test has a power of 0.54 to detect that P equals 0.07. Explain what this means. In part C, identify 2 ways to increase the power in part B. All right, so I want to try and answer A, B, and C. I do apologize. I did not give you guys a spot to answer this in. I'll have to fix that. I thought that I did, but I didn't. So write these on a piece of paper and we'll talk about it in about, let's say, 5 minutes we'll start with. All right, and if you have any questions, please let me know. All right, guys. So we're going to talk about these 3 questions here on side effects with errors in power. And again, we're going to look at the shared screen because I have that stuff already here. All right, so question or part A. A type 1 error would be finding convincing evidence that less than 10% of patients would suffer nausea after using the drug, when in reality at least 10% would. Right, so the type 1 error, right, is finding evidence, convincing evidence for the alternative when the null hypothesis is true. Right, type 2 is failing to find convincing evidence for the alternative when the null hypothesis is false. All right. So the consequence, right, the new drug is used on more patients, leading to excessive nausea. Right? If in reality more than 10% would get nausea, and we say, oh, well, this says that there's going to be less, well, more people are going to feel a little ill. Right? Type 2, failing to find convincing evidence that less than 10% would suffer from nausea, when in reality less than 10% would. Right? So in this case, it's failing to find that convincing evidence, and we will fail to reject the null hypothesis. Right? The consequence, the new drug is used less, even though it rarely causes nausea. Right? So the company's like losing out on their drug being used. Right? They're going to lose money. So that's our type 1 and type 2 errors in context. Right. If the true proportion of Alzheimer's patients who would experience nausea is really 0.07, there is a 50.54 probability that the results of the study would provide convincing evidence the true proportion is less than 0.1. Right, so again, that's the power of a test. It tells us the probability of a specific proportion, in this case, being the true proportion. All right. Well, not that it, sorry, say it again. It gives us the probability that the result of the study would give us evidence supporting the alternative, if that's the real proportion is 0.07. Right, and for part C, right, 2 ways we can increase the power. All right, increase the sample size or increase the significance level. Those are essentially the 2 go-tos. Right. Obviously, getting a larger sample size will give you more data and gives you a better opportunity to, essentially correctly get the right result. And increasing the significance level, right, gives us kind of like a larger target. Okay. And so that answers this question. Is there any questions? Is there anything I can clarify for you guys? All right, so that is the last slide of this Desmos activity. So then, yeah, that is essentially what we wanted to cover today. I do want to remind you, right, once again, resources for Chapter 9 and all previous chapters are in the modules, right? For Chapter 9, sorry, let me go back into the shared screen here. All right, for Chapter 9 here, we do have our Section 9.1 resources. We have notes and resources, practice problems, the activity. 9.2 and 9.3, we have our notes and resources. That includes like the study guides. We have our practice problems and solutions. All right, we have practice problems and solutions for 9.2 and 9.3. I really do recommend looking at these problems. They're a great opportunity to practice. Right. Also, I have the assessments ready for Chapter 9. We have multiple choice and the free response questions. Keep in mind, we haven't covered 9.3 yet. You're more than welcome to try to move ahead and look at the notes and resources. We'll start with 9.3 tomorrow. Hopefully we'll be able to get through everything we need from 9.3 tomorrow. And finish up this chapter. All right. But again, all this stuff is here. There's lots of good resources in here for you guys to check out, including like tutorials on how to use the calculator functions, which can be useful. All right. So please keep that in mind. Other than that, if you have any questions, comments, you need help with anything, with this lesson or chapter, previous lessons or chapters, please let me know. You're welcome to stick around right now as the class ends, and talk to me if you need to. Otherwise, we'll see you guys tomorrow, and have a great rest of your day.